Hello, everyone. Today we are going to talk about process capability analysis. Our requirement on the product quality is usually specified by the lower specification limit, LSL, and the upper specification limit, USL. If the quality characteristic of interest, X, is between the two limits, then the product is acceptable and it is classified as a conforming product. Otherwise, it is classified as a non-conforming product. What is specification limit? Specifications are the desired measurement for the quality characteristics. For the hard-to-bake process, which is an example we have seen, 1.5 plus minus 0.5 microns were the USL and LSL of the product. For individual product, we can decide whether it is conforming product or not based on specification limit. For process, we can compute probability that the process yields conforming product. Here is an example. For an injection molding process with LSL 75 and USL 85 for the major quality characteristic, after phase 1 SPC, the process is believed to be in control. After that, 50 manufactured parts are randomly selected and their values are recorded. The sample mean and sample standard deviation are computed to be 80.194 and 2.775 respectively. Then the process capability can be measured by the probability X between LSL and USL, which is around 0.928. This means that 92.8% of manufactured part of the process are conforming product, and about 7.2 of manufactured parts are non-conforming products. As you see, to analyze the capability of process to produce a conforming product, we need two things. The values of LSL and USL should be determined beforehand. And the data set reflecting the IC production of the process should be available. So we can say that process capability analysis of a production process is for measuring its capability of manufacturing conforming product by analyzing certain observed data that are representative of its production. Specification limits represent the voice of customer. They are set during the design phase of product or service. It involves not only engineering department, but also other customer related teams. On the other hand, the control limit represents the voice of the process. The control limits are set using a data set reflecting the IC production of the process. Consider a process where the mean and variance of the process can be estimated. And we want to estimate the fraction of non-conforming wafers produced. Then we can compute P to be 0.00035, which means about 0.035% of the wafers produced will be outside of the specifications. This indicates that the control limit as well as the specification limit both affect process capability. This example demonstrates how both the control limit and specification limit affect process capability. Here are two processes have same mean and specification limit. However, their process capabilities are different. Since the dispersion in the process on the right is higher, its process capability is lower than the process capability of the process on the left. There are 4 scenarios regarding to process capability. First, the process is in control and capable. The second, the process is in control, but it is not capable. The process is out of control, but it is capable, which is third. And last, the process is out of control and it is not capable. So let's see each scenario one by one. First, the process is in control and capable. This process will produce a conforming product as long as it remains in control, so it's okay. Second, the process is in control, but it is not capable. If the specifications are realistic, then an effort must be immediately made to improve process. Third, the process is out of control, but it is capable. The process must be monitored. Since the process is out of control, there is no guarantee it will be capable in the future. Last, the process is out of control and it is not capable. The process must be adjusted to be under control. After that, the capability analysis must be performed again. Now let me introduce a metric called process capability ratio to evaluate the process capability, which compares the control limit with the specification limit. The PCR is defined by the difference of the specification limit divided by the difference of the control limit. The difference of control limit is 6 sigma hat here if we consider 3 sigma limit. So in the previous example, if we plug the estimated values into the formula, then we can obtain the PCR to be 1.192. However, the PCR is limited in that it does not take into account where the process mean is located. Here is an example showing the limitation of the PCR. The process on the right should have a lower capability because it is not centered with respect to its specification limit. However, the values of PCR are same for two processes, although they are different. So to overcome the limitation of the PCR, the actual process capability ratio is proposed as the minimum between the distance to the USL and the distance to the LSL. These figures show 5 processes having same characteristic except the process mean. As we pointed out, the PCR values are all same for those 5 processes. On the other hand, the actual PCR enable us to distinguish their process capability. However, it does not mean that we don't need the process capability, CP. This example shows why CP and CPK both should be considered together. Here are 2 processes having different values of mean and dispersion. If we plug those values into CP and CPK formulas, it turns out that 2 processes have the same CPK, but the different CP. Therefore, to identify the properties of process in terms of capability, we may need to consider both CP and CPK together. Mathematically, we can show the relationship between CPK and CP by using the fact that minimum of A and B equals A plus B minus absolute value of the difference divided by 2, we derive the result about CPK as shown in the slide. As a result, CPK equals to 1 minus T minus mu, absolute value of T minus mu divided by D times CP, where T is the half of the difference between the USL and LSL, and D is the half of the difference between specification limit. This result implies that CPK is less than or equal to CP, and equally hold that equality hold if and only if mu equal to T. And CPK decreases when the absolute value of T minus mu increases. Okay, in this lecture, we talked about process capability analysis and 4 different scenarios we may face depending on process controllability and capability. Also, we discussed 2 types of process capability ratio, CP and CPK, and we derived their relationships. Thank you.